Meta has just released Muse Glimmer, a massive 30 billion parameter agent model engineered specifically to run on local hardware. Through 4-bit precision quantization, the entire model compresses into a footprint of under 20 gigabytes. That specific size matters because it leaves enough remaining memory on a single consumer GPU to actively run the model's working memory, or KV cache, alongside a dedicated perception encoder for multimodal inputs. To reach real-time speeds, Meta included the DFlash speculative drafter. A small network proposes 5 tokens at once. The main model receives this block and verifies correct tokens instantly in parallel, yielding a 3.1 times speedup on an RTX 5090. For immediate technical breakdowns of frontier models the moment they drop, subscribe to the channel. These specifications enable an always-on local agent. The model stays resident in your machine's memory, executing complex tasks without cloud latency or network access. Until now, running a local agent required a post-hoc compromise. The community would compress a massive cloud model to fit onto a standard consumer GPU. That community-led compression usually introduced severe friction. High-level agentic capabilities, the exact functions required for autonomous workflows, were often the first to degrade or disappear entirely. Muse Glimmer changes that dynamic. A frontier lab is now performing the compression themselves, end-to-end, treating local deployment as the primary engineering objective. The pipeline is explicitly designed to preserve specific agent behaviors, starting with the ability to execute precise tool calls using complex schemas. It retains active computer use, long-horizon multi-step reasoning, and automatic failure recovery, the ability to recognize an error and try a different path rather than just halting. This is a deployment reality. Meta shipped the weights under an Apache 2.0 license, allowing developers to download and integrate them locally today. The default origin of the local AI agent has shifted. It is no longer a hacker's afterthought, but a highly engineered product from the lab. The mechanism carrying the weight of that 20-gigabyte footprint is Meta's distillation pipeline. As shown here, it begins with an unreleased teacher model, Muse Spark. The process executes in 3 phases. In phase 1, pre-training, the student model undergoes logic distillation. Rather than just copying the finalized text output, the student learns from the teacher's full probability distribution. It absorbs the mathematical weights of every possible token the teacher considered. Phase 2 introduces mid-training, extending the context window of the material. This phase injects rich reasoning traces and highly agentic datasets into the learning stream. This specific mid-training phase is where the capacity for multi-step tool use is structurally embedded into the student. Phase 3 completes the pipeline with post-training. Here, supervised fine-tuning is layered over the model, specifically targeting coding and complex reasoning domains. It also employs a technique called on-policy distillation, creating a continuous feedback loop between the 2 models. The student generates its own action trajectories, and the massive teacher model evaluates and corrects deviations in real time, forcing the student to adjust. This 3-phase architecture represents a fully published end-to-end recipe designed specifically to transfer genuine agentic competence into a model small enough for a single GPU. For builders today, the release's most actionable asset is the 7-page evaluation methodology report. This document provides incredibly strict, reusable evaluation harnesses. For example, it defines the exact judging parameters, like using Gemini 2.5 Pro at a 0.75 pass threshold to grade outputs. It explicitly outlines the test conditions, detailing exactly how to run 500 tasks in MCP Atlas and 900 multi-step research questions through Deep Search QA. Any engineer evaluating local models can immediately lift this specification and use it to benchmark their own agents, completely independent of Meta's hardware. But that open documentation sharply contrasts with what Meta has kept entirely locked down, the massive teacher model. Muse Spark appears in the literature solely as a distillation target. Meta provides no parameter count, no statement of availability, and no plan for release. Because the teacher is missing, the distillation pipeline is heavily documented, but it is impossible to reproduce. Developers have been handed a finished product they can verify, but they are denied the underlying materials required to execute the recipe themselves. There is one vital caveat to understand before deploying Muse Glimmer into a production environment. The release's entire quantitative case is unquotable. The 7-page methodology document provides exhaustive detail on judges, sampling configurations, and exact run counts. But as you scroll through, you will find exactly 0 actual benchmark scores printed in the text. The official prose commits only to the phrase that the model performs strongly for its size class. For example, the methodology outlines a massive 949 scenario prompt injection safety evaluation. Yet, it provides no attack success rate figure to set expectations for an always-on agent with active tool access. It is a strange inversion for a model whose central pitch is benchmark-verified competence. Meta documented every single structural detail of the measurement, except the measurements themselves. The only place where numerical scores actually exist is a single comparison table pitting the model against Gemma 431b and Qwen 3.627b. These numbers are not in the text. They are locked inside a static image file pasted into the announcement blog. By Meta's admission, this table is a collage from 3 provenances. Blue rows come from Meta's internal test runs. Green rows rely on artificial analysis leaderboards. Red rows represent competitor self-reports. The final table is a patchwork. Furthermore, Meta acknowledges internal modifications to testing standards, such as employing a simpler matching algorithm for OmniDoc Bench than the official protocol demands. A table that mixes internal testing, third-party leaderboards, and competitor self-reports row by row breaks the fundamental rules of a controlled comparison. True verification will only arrive when independent community runs of the 4-bit weights on standardized tests like SW Bench and MCP Atlas hit public leaderboards. Meta's distillation pipeline remains a profound engineering achievement for local AI. But until independent data validates the image collage, builders need to budget for the promise and run the evaluations themselves.